Welcome to everybody. We've got another installment of Dr. Eigenstate Explains here, and in this installment we are going to be talking about something very fun. You'll remember in the last one we talked about the Big Bang, and I stressed in that video that what we call the Big Bang isn't really the beginning of the universe, that we've at least theoretically gone before that. And that is true. We have theoretically gone before the Big Bang. And what we're going to be talking about is how we've done that and what sort of physical models we have that explains it. And we do have one, and it is often referred to as cosmic inflation. And again, yes, I have really bad handwriting. Everybody's just going to have to deal with it. Some things you just can't change. So, I've said that we can go theoretically prior to the Big Bang, and that is what inflation is. What does it mean to go theoretically prior? Well, the thing with inflation, the thing with cosmic inflation and what it was and what it did, has never actually been observationally confirmed. We haven't observed that happen. That being said, the structure that we see in the universe today is thoroughly explained by inflation. Inflationary theory accounts for all of that. One of the first problems, I guess you could say, there were a number of problems with the hot Big Bang model, certain things that it just was not capable of accounting for. And inflation comes along and it solves all of these problems. The first one is referred to as the flatness problem. And this was the fact that the hot Big Bang model at the time was not capable of explaining why the geometry of space-time is flat. That is, that if you could draw space-time on a very large scale and give it, this is going to be, that is not going to, I'm going to have to do it this way. That didn't work. There we go. As you can see, the lines are what's called orthogonal to each other. They're supposed to be evenly spaced, but we're going to forget about that for the time being. But if you could draw space-time on a very large scale, the lines would be orthogonal. They would meet at 90-degree angles. They would be perpendicular to each other. So you would say that space-time is flat. So that if you were to, say, draw a triangle in the geometry of space-time, it would look like a normal triangle. However, if space-time were curved, a triangle wouldn't look like a normal triangle. Ignore it, it's a little bit curved. Space-time were, say, negatively curved, a triangle would look something like that. Its lines would be curved inward. If the universe were positively curved, if its geometry were positively curved, they would curve outward. The lines of a triangle would curve outward, so it would look more rounded. But a triangle looks like a triangle. So the geometry of space-time is flat, and that is what is meant when you hear cosmologists say the universe is flat, is that the geometry of space-time is flat. That we don't have to worry about curvature, or at least it's near perfectly flat. And inflation explains this. It explains it because it tells us that the universe expanded so much, so rapidly, that it just smoothed the geometry of space-time out, so to speak, and made it flat. So that is the first issue that the hot Big Bang model had, that it could not explain, that inflation explains. If the universe underwent a period of super rapid expansion or hyper expansion, whereby we would say it inflated, that would smooth out the geometry of space-time and make it flat. The second problem is called the horizon problem. And with this problem was that the hot Big Bang model at the time could not explain why two extremely distant parts of the universe look exactly the same, and why the cosmic microwave background is exactly the same in those regions. Because the amount of time it takes electromagnetic radiation to reach very, very distant parts of space-time would be a larger amount of time than the amount of time that the universe has existed for. So how do we explain how two very, very distant parts of the universe look the same? Well, if the universe underwent a period of hyper-expansion where it inflated, this would explain why very distant parts of the universe look the same, is because at one point they were very close together, and then inflation occurs and drives the universe outward, and these parts are now so far apart from each other that they couldn't look the same via traditional communication, which is going to take place at the speed of light. So inflation explains the horizon problem. Another one is called the monopole problem. And this is the fact that we don't observe magnetic monopoles. Inflation theory tells us that, well, they're rare to begin with, number one, but then inflation tells us that when inflation occurred, these small amount of magnetic monopoles that may have existed in the early universe would have been spread so few to so few and so far in between that they would have decayed before we had the opportunity to detect or observe any of them, and that's why we don't observe magnetic monopoles. Another one is that the inflationary theory helps explain the isotropy and the homogeneity of the universe. The universe is going to essentially it looks the same in all directions, and no matter where we would say that the universe is isotropic, and no matter where you measure the universe from, you're going to get the same results, the same physics, and it's going to look roughly the same. So we would say that the universe is homogeneous. Inflation can explain that too, by expanding the universe so much that it just looks the same everywhere. So these are some of the issues with the hot Big Bang model that it was not capable of explaining, and inflation explains those. And because the structure of the universe as we see it today is thoroughly explained by inflation, despite not having directly observed inflation take place, it is still a model that is widely accepted amongst cosmologists with only a few academic detractors. But I've been going on and on about all of the things that inflation helps explain and why it is a model that is adhered to by most cosmologists. I haven't really explained what inflation is. There's really three aspects of what happened during inflation. The first thing I want to say is that inflation is a period in the universe's history from about 10 to the negative 36 seconds to 10 to the negative 32nd seconds after t equals 0, where the universe underwent a hyper-expansive, it underwent a hyper-expansion. Its expansion rate was increased by an exponential factor, and the universe grew from about the size of a proton to about the size of a softball. It grew to a very, very large scale very, very quickly. In fact, the amount of expansion that's taken place in the universe from the end of inflation to now is a smaller amount than the amount by which the universe grew during the inflationary period. So that's the first thing I want to say, is that inflation is, well, the universe expanded very, very quickly. If this axis represented time, this axis is going to represent distance, and distance in space-time, then what happened is, we'll do a different color here. The universe was expanding and then underwent a hyper-expansive period, then ended, and the universe continued to expand. And that period right in there would be what we call inflation. That would have been the inflationary period. And like I said, there's three main aspects to this. There's the expanding metastable vacuum is the first phase, I guess you could say. The phase transition to the true vacuum state. And then the third one is called, if I could type properly, the slow roll and reheating. And we're going to go through these one by one and talk about what each one means. So, to start with, we have the expanding metastable vacuum. And that's essentially expanding spacetime. But and I just want to remind everybody that this is theoretical. This is what the current model states, though it hasn't been observationally confirmed. It's consistent, and it explains why we observe the universe to look the way that it does. But this is all very much theoretical. Nevertheless, expanding metastable vacuum essentially means expanding spacetime prior to the inflationary period, but more specifically, there is a particular type of energy field present in the early universe called the inflaton field. And this field was prior to inflation in a metastable state. So, to give an example of what a metastable state is, if you can imagine, I actually didn't need that, I can just do this. If you can imagine, you have a little bit of a trough here, but then you have a hill that rolls down to here, and you have a ball sitting here. You could say that the ball is metastable, in that if you give it a nudge and it rolls up to, say, the position that it's at now, eventually it will come to rest here. But if you give it enough of a nudge, then the ball will roll all the way down and rest here. So this isn't the true ground state. Down here is the true ground state. So you would state that this is the metastable state. And this energy field was in a metastable state. It wasn't in a true ground state. And that phrase is going to be important, because being in a true ground state is called being a true vacuum versus a false vacuum or a metastable vacuum. And so the universe was, this energy field, the inflaton field, was metastable and was expanding with spacetime. And eventually there was a phase transition to a true vacuum state. And that's the second part of what inflationary theory tells us. And essentially what happens is this field, as the universe is expanding, this field is losing energy, and it loses enough energy and sort of tunnels to a lower energy state. And what occurs during this phase transition to a true vacuum is the pockets of true vacuum are created, and the energy, the expectation value, the vacuum expectation value of that field, which is a quantity that tells us about the energy state of that field. And the vacuum expectation value for this inflaton field was fairly high, thus it had a lot of energy and made it metastable. Well, it begins to lose that energy as the universe expands, and space-time, in this vacuum existing in this metastable state in space-time, is very repulsive. It gives rise to a very repulsive force that pushes space-time outward, which gives rise to what we call inflation. And in the pockets of true vacuum that slowly take over this metastable false vacuum, the energy present in it, the vacuum expectation value, essentially turns into particles called inflatons, and those particles eventually decay into the standard model particles that we see today. So, in essence, you could say that the energy function, the potential energy function slowly goes down like that. And that would be the slow roll as it goes from a metastable vacuum to a true vacuum. And the reheating part is essentially during inflation, the expansion was so great that the universe was essentially supercooled during that state. And once inflation stops, the universe begins to heat back up as those inflaton particles decay into the standard model particles that fills the universe with a very, very hot soup. Excuse me, a very, very hot soup of quarks, gluons, and photons, maybe a few leptons, but mainly quarks, gluons, and photons. And that gets very, very hot as the universe is no longer expanding at this astronomically fast rate, this inflationary rate, and so the universe begins to heat back up, and that is called the reheating period. The slow roll essentially means that that potential energy function sort of rolls down slowly. So they call that the slow roll in reheating during the phase transition from a metastable vacuum to a true vacuum, essentially going from being in what looks like a ground state but isn't really a ground state all the way down to the actual ground state of that field, of that energy field. And thus it moved to a true vacuum state. And that is what inflation is. That is what inflation tells us happened. And rather that this process gave rise to a very, very powerful repulsive force in space-time that drove space-time apart exponentially, and that is what we call inflation. And the plasma that remained in the universe afterward eventually leads into all of the various epochs of the universes, the evolution of the early universe that I outlined in my last video. And that is essentially what inflation is. That is what the inflationary model tells us. And what I started the video off with, those observations that we make about the structure of the universe as we see it, essentially confirm inflation. Inflation is capable of explaining why our universe looks the way that it does, and then everything that I just finished explaining is the mechanism by which inflation occurs, at least theoretically. Again, we don't really have observations to confirm it, but it's mathematically consistent. It is consistent with other physical models that we have, and it gives rise to a universe that it gives us a universe that we see today. So it's capable of explaining why we see the universe that we see. So I hope you enjoyed this video. We've got a lot more coming out. We've done some cosmology. I might switch into some other topics. But for now, remember, per causam nos perfectum, or through reason we progress.